Okay, so we're going to start this one over just because, honestly, I can't remember where we left off in the last video, so feel free to skip ahead if you need to. What we're going to do here is we're going to square both sides, just like we did in the last example. And when I square a square root, that undoes or cancels out the square root. So I'm left with the radicand here, 2x plus 7. And when I square this guy, I need to actually square him. I need to multiply x minus 4 times x minus 4. And when I FOIL that, this is what I get, x squared minus 8x plus 16. Let's see if I can slide that over there so you can actually see that. So now I have 2x plus 7 equals x squared minus 8x plus 16. This is a quadratic, so in order to solve these guys, we need to set them equal to 0. So I'm going to subtract everything on the left side, and I get 0 equals x squared minus 10x plus 9. And then this is a factorable quadratic, so I can, now that I have it set equal to 0, I can use the zero product property. And when I factor, I'm looking for factors of 9 with a sum of negative 10. So I have a minus 1 and a minus 9. So if I FOIL this out, I'll get x squared minus 10x plus 9. Now, because each of these factors could be the 0, I set each one equal to 0. So in this case, x is 1. In this case, x is 9. Now, what can often happen with a quadratic is we get something called an extraneous solution. What that means is sometimes we square numbers and they end up being equal to each other even when we didn't intend for them to be. And I can go over this again in class because it's a little bit of a tricky concept. But what it basically boils down to is that we have to check each solution. So I'm going to check x equals 1 and I'm going to check x equals 9. And these checks aren't like good idea checks, they're absolutely necessary checks. So if I check x is 1, I'm going to rewrite this equation. Instead of x, I replace it with a 1. And add 7, and I want to know is that 1 minus 4. So I'm replacing the x's in this equation with a 1. This gives me radical 2 plus 7 is 9. And does that equal 1 minus 4, which is negative 3? Radical 9 is 3, and 3 does not equal negative 3. So this is a thing where, like, this is a false statement, but if I actually squared both sides, I'd get 9 equals 9, which is true. So it's one of these kind of freaky things that happens where when we square numbers, we might get something that's true, even though they're not really supposed to be true, okay? So this is no. That does not check, okay? So sometimes I just put a little x next to it. Now we're going to check x equals 9. And 2 times 9 is 18 plus 7 is 25. And 9 minus 4 is 5. And radical 25 is 5, and 5 equals 5. So that one does check. So what that means is we go back over here to our solutions. And we say, okay, this one checked, it's good to go. This one did not, so we gently cross it out. I'm not erasing it, I'm just crossing it out, and underneath I'm writing the word extraneous. And you want to think about that means like extra, like it's an extra solution, but it doesn't actually work. Okay, in this case we have a fractional, like a rational exponent here, 3/4. So I want to get rid of that, and there's kind of a creative way to do that. So the first thing I want to do is get rid of this minus 2 by adding 2 to both sides. So now I have 3x, and this whole thing is raised to the 3/4 power. And this equals 27. Now, if I want to undo a 3/4 power, that's like saying this is the cubic, or the 3x raised to the 3rd power, but then the 4th root of it. So I want to undo 4th root and undo 3rd power at the same time. So what I'm going to do is I'm going to raise this to its reciprocal power. That's because 3/4 raised to the 4/3 power, these cancel each other out. So the cubed root of a cube, 4th power of a 4th root, and they end up making just a power of 1. But remember, anything we do to one side, we have to do to the other. So we're raising both sides here to the 4/3 power. So here we get 3x, okay? And here we get the cubed root of 27 to the fourth power. So sometimes it helps to write it like this. So the cubed root of 27 raised to the fourth power. And that allows me to say 3x equals, now we know the cubed root of 27 is 3, and 3 to the fourth power we can evaluate. 3 to the fourth power is 81. And I can divide both sides by 3, and we get x equals 27. So to check this, we just plug it back in. And this one shouldn't have given us any extraneous solutions because we didn't have to like square both sides, but we did raise it to the fourth power, so you never know. So I'm going to plug in 27 for x. We're going to raise that to the 3/4 power, subtract 2, and hope to get 25. So this has to be raised to this power first, okay? I'm sorry. That's 3x to this power. So these have to be multiplied first. So that's 81 to the 3/4 minus 2 is 25. The fourth root of 81 is 3. And 3 cubed is 27. And 25 is 25. So that's a good check. This example is a lot like the one that we had done earlier. I want to say maybe example 3. So this 1/2 power means the square root. So I could also write the equation like this, and it means the exact same thing. So if I write it like this, I'm going to square both sides to get rid of the square root here. And when I do that, I get x plus 12 equals x squared. So again, I have a quadratic here, and I need to set that equal to 0. So I'm going to subtract these terms from both sides. And now I want to see if it's factorable. So I'm looking for factors of 12, and because that's a minus, the signs are going to be different, which means they have a difference of 1. So I'm thinking 3 and 4 have a difference of 1. So because that's a negative, my larger number goes with my subtraction sign. And then I have my two factors, one of which could be the 0. So I separately set them equal to 0. So x can be negative 3. Or x can be 4. One of these is going to check, one is not. And I know that because I'm looking right back here and I'm thinking, there's no way that I could plug in a negative here and take a square root of something and have it come out negative. So I know that negative 3 is going to be extraneous, but just for the due diligence, we'll actually do a real check here. So I'm going to check x is negative 3 by saying negative 3 plus 12 to the 1/2 power is negative 3. This is 9 to the 1/2 power, which is the square root of 9, which is 3. 3 does not equal 3. So that negative 3 is extraneous. When I check the x plus 4 over here, or I'm sorry, x equals 4. Whoops, I went ahead and added that. 4 plus 12 is 16. The square root of 16, which is the same as 16 to the 1/2 power, is 4. And 4 equals 4, so that does check. So this is my final answer here, where negative 3 is extraneous, but x does equal 4. To solve an inequality, you treat it a lot like an equality, or an equation. So we'll just start that approach here by adding 4 to both sides. And that gives us 3 radical x is less than or equal to 12. Now, in order to isolate my variable here, I'm going to divide both sides by 3. Because it's a positive 3, I don't need to worry about flipping that symbol like I normally would if I were solving an inequality. So I have radical x is less than or equal to 4. And lastly, I need to square both sides here. So I get x is less than or equal to 16. So what I want to do here is I really want to be careful with this check and make sure that that's the only possible solution. So what I'm going to do is I'm going to take the sort of x does equal 16 piece and see if that checks out. So if I plug in a 16 here, I end up with 3 times 4, which is 12. And 12 minus 4 is 8. And is 8 less than or equal to 8? Yes, it is. So that checks out. And then I also want to check a number that actually is less than 16 from this inequality. So if I test a number less than 16, I could maybe test, let's see, we want to be able to plug in something here that's a perfect square. So I'm going to try 9. So when I test a 9, which is less than 16, I get 3 radical 9 minus 4 is less than or equal to 8. So that's 3 times 3, which is 9. 9 minus 4 is 5, and that is less than or equal to 8, so that works out great too. So the 16 works, the 9 works, so far so good. However, there's this other thing we need to consider, which is that the number we're plugging in is going to